Chairman. Today I will talk about low temperature water activation and cationic hydrogen production. We all know that the society is transforming from the carbon-based cycle gradually to the new energy cycle such as bacteria or the hydrogen cycle. But where can we get the hydrogen? The two of the molecules are most important for hydrogen production. The first is the methane, the second one is water. But for methane, we have a limited reserve, but for the water, we have very large reserve, but it is chemically inert. And also, the challenge is how can we activate the water molecule at low temperature? The second one is how can we improve the efficiency of the activation? The third one is can we build the cationic cycle to get the hydrogen release out? Currently, lots of the reactions are related with the water activation. For example, for everyone know, HER reaction, or the water gas shift reaction, or the methanol reforming hydrogen from biomass, or the methane steam reforming that is largely dependent on industry, right? All these reactions are very much related with the water activation process. But is the water very difficult to be activated? Actually, it is not. Even in the pure water, we can see proton can be generated even at very low temperature, but the concentration of the proton is very, very low. And also, it is a kind of the heterogenetic splitting. So you can, from this kind of the water activation, you can just get the proton and hydroxy. You cannot get the hydrogen gas out. So on the catalyst surface, this process is promoted definitely. For example, everyone knows titanium oxide is very good for water activation. For example, Lubinsky has tried to study the water dissociation over titanium oxide surface. He found that the water dissociation is very easy. It has just have a barrier of 0.35 if. It's very easy to happen. And the product of the water activation, you can see the water is absorbed on titanium in the initial state, titanium atoms. In the final state, is one of the proton is transferred over the oxide of the titanium oxide. The result is the water activation is formed two hydroxy on the surface. So although water is activated, you cannot get the hydrogen out because the product for the water splitting is proton, right, and hydroxy. So how can we get the gas or hydrogen molecule out? It is easy. We have a photocatalytic hydrogen production approach and also electrocatalytic approach. For example, if you have a water activated, you have a proton, then if you have a sunlight, for the electron hole separation, you can have one electron generated and it is transferred to the catalyst surface, and if your proton is get one electron, it can become the negative or neutrally hydrogen absorbed on surface. If you have a two neutral absorbed hydrogen atom, it will combine to release the gas phase hydrogen out. So it is easy. The K is you need an electron generated from the photocatalytic process. For the electrocatalytic process, it is similar. The proton activated from the water splitting need an electron from the electrode. Then it can combine together to get the hydrogen gas out. But the problem, for all this process, you can see we cannot get directly without the electron from the photo or electron catalytic process, we cannot get the gas phase hydrogen out. So the problem for us is, can we get, for the thermocatalysis, can we get the hydrogen gas out? Can we get the hydrogen water molecular homolytically activated? And also, can we get the hydrogen gas out? Is it possible? Actually, in almost 100 years ago, our pioneer, Iran Langmuir has studied this reaction. This is water molecular activity on platinum surface. He finds that at 1,300 degrees C, water can split and produce hydrogen gas as well as oxygen gas. I think this is in 1980s, people confirm this as well. But if we want to get another thing I need to, remind you is even the Langmuir's paper, it has a very low citation, but it is important, surely. So the problem is, if we want to get the hydrogen gas out from our thermocatalysis, we need very high temperature. So can we get it at no temperature? Actually, there also our parallel already show us some of the hints. Professor Michel Boudard, and in 1970s, he used transition metal carbide. The transition metal carbide has a similar electronic structure with a noble metal such as a platinum. But the difference is that it is a asymmetric surface. So for the asymmetric molecules such as water or methane or other hydrocarbon, it has a more capability to activate molecules. Under this and that time, Michel Boudard used a metal tungsten carbide to activate hydrocarbon, right? Under this consideration, we can say we can, tune the electronic structure and also the geometry of our molybdenum carbide by insert different degree of the carbon inside this molybdenum carbon canists. Once you have a proper concentration of the carbon, you have a right electronic structure and a right geometry structure, then possibly you can have your water activity and even at very low temperature. Fortunately, I have a find by collaborator, Professor Jeroen van Poffen and also Professor Luca is here. And they have ambient pressure, near ambient pressure XPS. In my university, we have a ambient pressure XPS, in-house ambient pressure XPS, also the synchrotron ambient pressure XPS in Shanghai synchrotron facility. But this one is unique because they have a very small detector chamber, very similar to the plug flow reactor. That using this kind of the reactor for near ambient pressure XPS, you can rule out the influence of some of the, such as water or salty on your chamber. It can easily to be treated. So this chamber is very much like our fixed plug flow reactor. Using this ambient pressure XPS, we find that this is another benefits of XPS is you can see almost all the elements on your surface, such as oxygen, carbon, molybdenum, PT. We use alpha molybdenum carbide supported PT for the measurements. We can find that after activation, for this residual oxygen, once you dose water inside your chamber, this is a gas phase water, you can immediately see hydroxy appeared on its surface. That means at no temperature, room temperature, water is dissociated. So, but the dissociation does not mean that hydrogen could be produced, right? Because we already know titanium oxide surface, so although it has a very low reaction barrier, it just forms 2 hydroxy instead of the hydrogen gas. We use mass spectroscopy in parallel with ambient pressure XPS. We can find, say, once we have the water inside our chamber, immediately we can see the hydrogen gas release out. This means that water molecular can be activated at very low temperature, and the hydrogen gas can be produced directly from our canister surface, that is the molybdenum carbide. But the problem is, if this thing is so easy to happen, then why people are trying so difficult to use electrocatalysis or photocatalysis to splitting the water? because your thermal catalyst can already activate water and no temperature, right? So let's check this this model. You can see besides the formation of the neutral hydrogen, then the gas phase hydrogen, you always get hydroxy on the surface as well. So the formation of the hydroxy is stoichemic. That means once your surface of molybdenum carbide have 1 nanometer of hydroxy, the production of the hydrogen should stop. You can see here, gradually it stopped, right? So how can we constitute an efficient hydrogen production cycle then? So our approach is to construct interfacial catalysts. Using molybdenum carbide, you can activate, we can already show that, you can activate the water and produce hydrogen and hydroxy on the surface. Then we can put nanoelemental, for example, platinum, gold, or nickel, whatever, on its surface. The carbide will modulate the structure of your supporting mantle, and more importantly, it constitutes the interface between carbide and your second mantle. So another reactant, for example, methanol or CO or the biomass molecular can associate on the surface of the second mantle and reforming with your hydroxy produced in the first step of the water activation. Then it leads to the formation of CO2 and hydrogen, right? Once this cycle is completed, then you will recycle your molybdenum carbide surface back. It is back to water activation again. It constitutes a catalytic cycle for high efficient water production, hydrogen production. I will use a gold supporting alpha molybdenum carbide and as an example for this. You can see gold is used to associate CO, and water is activated on molybdenum carbide, and any interface is a reforming reaction to regenerate the molybdenum carbide surface. This reaction, water-gas shift reaction, you all know, it is actually favoring no temperature. However, it's like nitrogen ammonia synthesis is also favoring no temperature, but the reaction barrier is high, so you always need high temperature, right? For this reaction, if we can get the reaction done in low temperature, we can get the benefits of the high reactivity and also the high equilibrium and low temperature. Previously, there are some of the very good candidates. For example, gold supporting server, that is, I think is this Maria Stephanopoulos, or the IR1 supporting iron oxide, and 500 and 300 degrees C, the mental normalized activity is 2.3. The best one is a sodium modified gold catalyst, I think is this one. It has a really low temperature activity and 150 degrees C. The activity is 0.06. But in using our strategy to construct the interfacial catalyst using molybdenum carbide, alpha molybdenum carbide as a support, it actually not just a support. It is a catalyst itself as well. We can see even at 150, our activity is around 20 times higher than the previous base catalyst. Even for the low temperature, such as 80 degrees C, we have 0.15. Catalytic activity. You can see that actually this is the reaction temperature and this is the CO conversion. Actually, and low actually alpha molybdenum carbide already have around 65% of the CO conversion and 250 degrees C, but it's decreased, further increasing the temperature. However, if you support it, you construct interfacial catalyst, support the gold on its surface, you can have a very high reactivity, very high conversion and low temperature 120 degrees C. But the conversion is nothing. The most important is the TOF. Compare the TOF, this kinase has the highest activity compared to the reference kinase. Another concern of people is the molybdenum carbide, because the reactant CO and also CO and hydrogen, or the water and also carbon dioxide is a kind of the soft oxidant. It could oxidize your molybdenum carbide, lead to the deactivation. Actually, on this alpha molybdenum carbide is at its high temperature, the decaying of the activity, I believe, is because of the oxidation of the molybdenum carbide to molybdenum oxide. We use a synchrotron X-ray diffraction, find that indeed it will be transformed from the molybdenum carbide to molybdenum oxide. But at low temperature, such as below 250, it is safe. So we can use it at a relatively low temperature if we can get the high reactivity. So for the ambient pressure XPS, if we have the hydroxy on the surface, it can react with if you indose CO inside, you can react with your gas phase CO or sorted CO and produce another hydrogen and recycle back your molybdenum carbide. Using this TPSR, we can find that for the alpha gold supporting alpha molybdenum carbide, if you dose water inside the system, you can immediately see that this is at room temperature, immediately see the formation of the hydrogen. Then you can introduce the CO inside and increase the temperature, and 325 degree, the formation of the second hydrogen already appeared, accompanied by the consumption of the CO and production of carbon dioxide. But so it could regenerate the molybdenum carbide surface. But if it is the same, it's a gold supporting the silica, you can see neither in the first step there is no production of the hydrogen, or in the second step there is no production of the hydrogen as well, just the desorption of the water when you absorb it and in the first step. So this shows that alpha molybdenum carbide is really very active, and using this interfacial strategy, you can construct efficient kinase that can be used for the hydrogen production. So we want to study the ability of the water activation over alpha molybdenum carbide. We use a double channel transient kinetic analysis, and we do the two switch. The first one is a four switch. Is a switch from argon to hydrogen, then go back to argon, then go back to water, and go back to water, and go back. Then immediately when you switched from the argon to water, immediately you can see the formation of the hydrogen, right? And the water appeared in a relatively slow, because they are absorbed on the surface. In the second, the switch, you can see there is no production of the hydrogen. The difference between this water line and that of the reference line is reversible water absorption. And the difference between this line and this line is irreversible water absorption and reversible water absorption, the sum. So you can get the reversible water absorption from these two experiments. We can see that, and we normalize the irreversible water absorption on the molybdenum surface. We find that even at 30 degrees C, the molybdenum surface is occupied by water molecular, irreversible or sorpted water molecular already. And of this water, or sorpted water, irreversible water absorption, 2/3 has been transformed into hydrogen. This means it is a really very capable catalyst for water activation and hydrogen production. And 100 degrees C, you can say almost 100% of the water absorbed has been transferred into hydrogen out. So we can use this concept to build other hydrogen production systems, such as methanol reforming with the water. This reaction is very important because in the, you can, if you have additional hydrogen, you can synthesize methanol from this reaction, and you can transfer your methanol into any place you want, because hydrogen is very difficult to transport. And then into the desired place, you can do the reverse reaction, that is the methanol reforming with the water to get the hydrogen out. Then you produce carbon dioxide as well. But in the whole process, it is carbon neutral, right? So using this concept, we can do, especially combined with a fuel cell, you can do, for the communication station, for the charge station, and also island energy station, you can use it for all kinds of these kinds of the things. Using similar concept of the individual kinds, we can disperse, PT over molybdenum carbide, use PT for methanol activation, and we'll use molybdenum carbide for the dissociation of the water, and the interface is corresponding for the reforming reaction of the CO and the hydroxy, right? For this kinase, we get a record high TOF compared to previous reports. So I will skip this one. So is it possible to get even better kinetics? We already know the efficiency lies how the molybdenum carbide surface can activate or software active water. The first one is. The second one is reforming. I think reforming is right determining steps. So if you want to increase the reaction rate for the reforming, besides the E term, energy term, the prefactor is important as well. To increase the prefactor, you need to increase the density of your active sites, right? So our strategy is to how can we increase the density of the active sites? The active sites is the interface of the, for example, PT supporting alpha molybdenum carbide. Previously, in our paper, we find that if we increase the loading of the PT to 2 or 3 already, we can find the diffraction peak of the PT already. So and 7%, you can say it become a relatively large PT particles. But how can we get a better disperse of the PT species? It's very easy. For molybdenum carbide, you can treat the surface with a hydrogen, high temperature hydrogen. You can remove some of the carbon, and then there are more vacancy on the surface. And at that time, you introduce your platinum into your system. You can say that even at 8% of the PT, there is almost low PT diffraction peaks. That means the PT is highly dispersed over the surface. We check it by TM. We find that at 8% of the PT1 species is atomic dispersed PT, and very small, PT clusters, and 2% of the PT supporting molybdenum carbide almost all atomic dispersed PT species. The population of these species is demonstrated here. Using these kinetics, we can further increase the reactivity. The mental normalized over PT. the activity is the highest, much higher than our gold kinase and all these oxide-supported kinases. Notice that this is not a linear, X, right? So, for the United States DOE, they set the catalytic activity threshold for hydrogen production. The limit is this one. Previously, no can even our gold supportive and alpha molybdenum carbide cannot exceed this limit, but only these kinases have this limit, can exceed this limit. Another, besides this is normalized over your mental. Another important thing is actually mass-specific activity, because you can use a very small amount, such as 0.01% of the mental, and calculate the TLF to be very high, right? But the overall mass-specific, average over the mass of the kinase is very low. That is nonsense. So we calculate our mass-specific activity of this kinase still is the highest in the currently reported. So for the third issue is normally, by our understanding, for example, for reforming reactions such as water gas shift is like this. Water is dissociated to hydroxy and hydrogen, and CO or sorbent on the another side of the interface will react with the hydroxy to produce CO2 and hydrogen. So for this scheme, and CO is not dissociated. These just need to be absorbed on the non-elemental. So does this right to be? We have a new silica instruments built by one of my PhD students, Zhang Mengtao. It is completed. It's very complicated to do the silica experiments. I just show you the conclusion. The conclusion is, and our reaction temperature, besides the previously think that non-dissociation CO reforming with the hydroxy mechanism, there are the channel for CO dissociation. CO is actually dissociated as a carbon on molybdenum carbide surface and oxygen. And this carbon could react with the hydroxy or oxygen to form CO2 and additional hydrogen out. This is another channel compared to the conventional reaction channel. But it is the contribution of this channel is just around 20%. Still, the conventional channel is a main contributor to these reactions. This kind of the kinase, we can use it for a lot of the process. For example, in the industry, we have a lot of the byproduct gas, such as the gas contain lots of the CO or a small amount of the hydrogen. It could be used as a hydrogen gas source for the hydrogenation reaction, but the existence of the CO will poison your PT kinase, right? However, using our concept, we can use this crude hydrogen or the byproduct, gas contain large amount of the CO to do hydrogenation reaction, and the kinase is not being poisoned, especially in the coexistence condition with the water. Also, using this reaction, we can do CO react with the water to produce hydrocarbon. This is a direct reaction. And then surely, because the hydrogen is produced by organ shift, is extracted from the water, so you will get lots of the production of the CO2. This is our GC mass specs. This is our GC. You can say indeed from CO and hydrogen, CO and water, we can produce the carbon, hydrocarbon up to the carbon number of more than 50. So, but another problem for this reaction is the stability. As I already told you, we can improve the stability by put the second menthol to reforming the catalyst back. But still, for example, in the Misono reforming reactions, we can find that for the stability test for the first hour, the TOF is 18,000, but for the 11th hour, it's already 6,000. It's declined 62%. It's declined very quickly. So how to improve the stability is our aim. Now we have some of the idea because limited of the time. So I could tell you the next time. So now the but I will show you the result. The TON number, I think this is a good measure for the stability or the lifetime of the catalysts. For our PT molybdenum carbide, the TON number already is, I think this is a 15 million, right? It's already 15 million in 800 hours. So it is a very large number. So these kinds of the construct for the interfacial catalysts could be, has a very good stability. So I will go to my last stage. For all the work are done by my students, PhD students and undergraduate students. I need to thank all the funding providers such as Senhua, Senfield, China, and also the synchrotron time, Shanghai, Beijing, or Hefei, Spring 8, IPS, PSI, and also Arba, and my collaborator such as Li Weixue, who is in the conference, Berwick Carson is in conference, Zhou Wu, and other people. Thank you very much.